morning students. In today's class we will move on to problem number 6. A power system shown in figure has a dead short circuit at the midpoint of the transmission line. Find the short circuit current for LG fault, LL fault and LLG fault. Assume the machine is operating at its rated voltage. Neglect the pre-fault current. The reactances in per unit are on the same base. This is the given power system network having two machines, two transformers and a transmission line between the two transformers. The reactances given are in per unit with respect to a common base, so no need to calculate the reactance values again. Step 1 is to draw the positive, negative and zero sequence networks of the given power system. So given the fault is occurring at the midpoint of the transmission line. So we know for unsymmetrical fault analysis, to draw the Thevenin's equivalent positive, negative and zero sequence networks, we need to draw it with respect to the fault point and reference. Okay, so we equally divide the transmission line reactance into two halves. One half on the right hand side and the other half on the left hand side to the fault point. Okay, so since for fault analysis, the Thevenin's equivalent networks are drawn with respect to the fault point and the reference, we divide the given transmission line reactance into two halves. So we get x1, x2 is equal to j.05 per unit, x0 is equal to j.4 by 2, which is j.2 per unit. So now draw the positive sequence network. This is the equivalent circuit of a generator. This is the reactance of transformer 1. This is one half of the transmission line. This is the reactance of the second half of the transmission line. This is the reactance of the transformer. This is the reactance of machine 2. This is the EMF source of machine 2. Okay. And copy down the reactances given from the power system network. Then draw the negative sequence network. So in the negative sequence network, we don't have the voltage source. And given the negative sequence network, negative sequence reactances of the machines are different from the positive sequence reactances. Okay, so carefully you have to copy down the values of the reactances. Then draw the zero sequence network. This is the machine 1 reactance, machine 2 reactance, transformer 1, zero sequence reactance of half of the transmission line, zero sequence reactance of remaining half of the transmission line. This is the zero sequence reactance of the transformer. Okay, so note down, for the two machines as well as the star neutral point of the transformers, we have the neutral point solidly grounded. Okay, so that is why we are not including Xn anywhere, 3 into Xn in the machines. And coming to the transformer configuration, we have delta star. So delta side, series switch is open, shunt switch is closed. Okay, and star, since it is solidly grounded, we have the series switch closed and shunt switch open. So coming to this transformer, second transformer, delta side, series switch is open, shunt switch is closed. Okay. So after drawing the three sequence networks, we will move on to step 2, drawing the Thevenin's equivalent positive, negative and zero sequence networks. Okay. So for drawing the Thevenin's equivalent positive sequence network, we need the pre-fault voltage. So in this problem, they had given neglect the pre-fault current. So since the pre-fault current is absent, we have to consider the pre-fault voltage or the Thevenin's voltage as VPF is equal to 1 angle 0 degree per unit. Okay. So for finding out the positive sequence equivalent impedance, short the voltage sources and redraw the positive sequence network. Okay, because we want the equivalent impedance at the fault point. So if you see, with respect to the fault point, there are 3 series connected reactances on the left hand side and 3 series connected reactances on the right hand side of the point F. So the reduced circuit will be like this. So the equivalent impedance or the reactance at the fault point is the parallel combination of j.475 and j.425. So when you calculate, you will get the equivalent positive, the Thevenin's equivalent positive sequence impedances j.2243. So with this VPF and Z1 equivalent, we draw the Thevenin's equivalent positive sequence network. We draw the Thevenin's equivalent positive sequence network. Okay. So now let us move on to Thevenin's equivalent negative sequence network. Yeah. The reactances of the generator or the machine is different from the positive sequence network. So it is J0.2, J0.15. So the other equivalent circuit remains the same. So to the left hand side we have series combination of 3 reactances. On the right hand side also we have the series combination. So by adding we have J0.375 and J0.325 in parallel with respect to the fault point. So when you calculate, the Thevenin's equivalent negative sequence impedance Z2 will be J0.1741 per unit. So with this equivalent impedance, we draw the negative sequence network. So this is the Thevenin's equivalent negative sequence network with Z2 equivalent. Next we have to draw the Thevenin's equivalent zero sequence network. So for drawing the Thevenin's equivalent zero sequence network, on either sides of the transformer T1 and T2, we have delta configuration. So at delta configuration, at the delta side of the transformer, we have the series switch opened. Okay. So the reactance, the machine reactance will come beyond the open series switch. Okay. So do not consider those machine reactances in drawing the equivalent impedance circuit of zero sequence network. Okay. So if you go back to this original circuit, original zero sequence circuit, see, beyond the delta, at the delta side the series switch is open. So don't consider this J0.05 and this J0.05 because we have open over here. Okay. So this is how we have to draw the equivalent impedance circuit of zero sequence network. Okay. So we have J0.3 in parallel with J0.3. So when you calculate, you will get equivalent zero sequence reactance Z0 equivalent is equal to J0.15 per unit, and with that value we have drawn the Thevenin's equivalent zero sequence network. Step 3 is to calculate the short circuit fault current for the given type of fault. So case 1, LG fault. So we know for LG fault, connect all the 3 equivalent sequence networks in series. Thevenin's equivalent positive sequence network, Thevenin's equivalent negative sequence network, and Thevenin's equivalent zero sequence network. Write down the values from the equivalent circuit. Write the formula for IA1. IA1 is equal to VPF divided by Z1 plus Z2 plus Z0. On substituting and calculating, we will get IA1 as minus J 1.8234 per unit. Therefore, the fault current IF is equal to 3 IA1 minus J 5.47 per unit. To get the magnitude alone of the fault current, it is 5.47 per unit. Okay. So since the generator ratings or the common base values are not given, no need to calculate the actual values of the fault current. Leave the answer in per unit. So let's go to the second type of fault, that is LL fault. So in LL fault, the positive Thevenin's equivalent positive network and Thevenin's equivalent negative sequence network should be drawn in parallel. Okay. Copy down the values of the reactances from the equivalent circuits. Now IA1 is equal to VPF by Z1 plus Z2. On substituting, you will get minus J 2.51 per unit. The formula for fault current is IF is equal to minus J root 3 IA1. We will get minus 4.347 per unit. Magnitude of fault current is 4.347 per unit. The third type of fault is LLG fault. So in LLG fault, we have the Thevenin's positive sequence network, Thevenin's equivalent negative sequence network, and Thevenin's equivalent zero sequence network, all 3 in parallel. Okay. So write down the formula for IA1. Substitute the values. You will get IA1 as minus J 3.28 per unit. And IA0 is equal to minus IA1 into Z2 by Z0 plus Z2. You will get IA0 as J 1.762 per unit. And the value of the fault current IF is 3 IA0, which is J 5.286 per unit. Only the magnitude of fault current in per unit is 5.286 per unit.